So yesterday we have derived the equation for time period of a spring mass system. Okay. So a spring mass system, when its mass is displaced from its equilibrium position or the mean position, if it is displaced and you leave it like you just displace it and leave it like that. Don't keep on applying the force. Just displace it and leave it. So if that happens, then in the absence of air resistance, the mass will keep on oscillating about the mean position. So for that particular oscillation, ideal oscillation, we have derived the time period, frequency, and all that, and then we have solved a numerical. Okay, so uh, so after spring mass system, today we will discuss about the simple pendulum. Okay, so how to derive the time period of a simple pendulum, that we'll discuss. Okay, so you can see a simple pendulum. This is your pendulum. It is hanging from a rigid body, which won't deform. It's a rigid body. So at the mean position, this is your pendulum. What you do, you just uh, pull the string a bit. Don't pull the string, just pull the pendulum a bit and take it to this position. Okay, then you release it. So if you release it, the simple pendulum will start oscillating about this point. It will go this point, come back, and then it will overshoot the mean position. Then again it will come back and it will start oscillating. So what will happen? This simple pendulum will keep on oscillating. It will keep on oscillating about the mean position. So the simple pendulum will keep on oscillating about the mean position. So if this is theta, this is also theta. Okay. So it will keep on oscillating. Okay. Now our job is how to find out the time period of this simple pendulum. There can be a number of, you might have done an experiment in your college on time period of simple pendulum. So how to derive the time period of a simple pendulum. So you can see here, you consider this blue color mass. Okay. So on this mass, what is the force acting? mg. That is the force, gravitational force acting on it. And this angle is theta, right? If this angle is theta, this line, this red line is parallel to this line. Okay. And like this is parallel to this. And anyway, this is the extension of this. So this angle is also theta. Okay. If this angle is theta and so this angle is theta, so there is a force. You will have two component of this force mg. So one component is mg cos theta. So you know any system. So if a force acts like this, and if this is the angle, then this force is f cos theta. This force is f sin theta. So because of the same principle, this force is mg cos theta, this force is mg sin theta. Okay. So this force and this is called the moment arm. Okay. See here we are getting into the torque concept rather than getting into force concept. So a torque mg sin theta and the moment arm is L. Okay. The force into distance. So you know torque is nothing but force into distance. Okay. So you know the concept, like suppose I have a door. Okay. So I have a door. Okay. Then I am applying some force here. Okay. So the torque will be depending on the moment arm, the distance, which is nothing but a moment arm. So let us say there is a cross. So you are applying a force perpendicular to the plane of the door. So you are applying a force and the moment arm is equal to d. So a torque F into d is acting there. So the concept of torque is like that. Like torque will called angular displacement theta. Force will cause linear displacement x. Okay. So this torque. So if you apply a force here, you have to apply double the force to create that kind of torque. If you are applying force here, you have to apply, let's say this is d by 2. You have to apply 2f force to create the same amount of torque. See, to create a particular angular displacement, you need to apply more force if the moment arm is less, right? So in torque, moment arm has a big role to play. So the more from this support location, if the more is the distance, the lesser is the force you have to apply. So to open a door, so if I am opening at the edge of the door, you will apply less force. But if you are trying to open it at the middle of the door, you will apply more force. So distance or moment arm has a big role to play. Okay, so in linear thing we call it as force. In angular thing, force will become torque. In linear thing, distance is x, angle will become theta. In linear thing, velocity is v, whereas in angular thing it will become omega. In linear thing, acceleration is a, whereas the corresponding angular thing is alpha. So this is one is linear motion, one is angular motion. So here we are dealing with angular motion. Okay. So your torque is equal to F into D, that is equal to mg sin theta into L. Okay. So that is mg sin theta into L. Then we know torque is like the way force is equal to ma, torque is equal to I into alpha. So equivalent of in linear motion, equivalent in angular motion, equivalent of mass is I, which is moment of inertia. I. Okay. So equivalent of mass in linear motion, in angular motion, the equivalent of mass is I. Okay. So a torque and equivalent of acceleration is A, alpha. So ma, so equivalent of force is torque in angular motion. So torque is equal to I into alpha. Okay. Then you know force is equal to ma, that is okay. So torque is equal to I into alpha. Okay. Then uh, so how much is, so this is one equation, and how much is this torque we got, that is the force into distance. So mg sin theta into L. Okay. So now these two equations you are equating. Okay. So how much is alpha? Mg sin theta into L by I. I is the moment of inertia. We will get into it. What is moment of inertia? Okay. So your alpha is equal to mgl into theta by I. So sin theta becomes equal to theta. So in your limit you have studied limit sin theta by theta when theta tends to 0 is equal to 1. Right? So when it becomes 1, that means sin theta is equal to theta. So when the angle is very less, sin theta becomes equal to theta. So in this case, you can imagine the angle to be very less. So sin theta will become equal to theta. So this sin theta you have written as theta. Okay. So your this becomes alpha is equal to mgl into theta divided by I. Okay. So uh, so in linear motion, acceleration is omega square x. Okay. In angular motion, this is the angular acceleration is equal to mgl by I into theta. So if you equate the linear motion, a linear motion with angular motion, this is the expression for linear acceleration. Alpha, this expression is the expression for angular acceleration. So if you just compare these two equations, let us say 1 and 2. So this x and theta are similar thing. X is linear displacement, theta is angular displacement. So if you take these two are equal, alpha and a are equal, so then omega square becomes equal to mgl by I, right? Because this is angle, this is distance, the same. So omega square equal to mgl by I, right? So omega square is equal to mgl by I, And what is I? I is moment of inertia. Normally it is mass into distance square, mr square. Okay, moment of inertia, you always remember it is equal to mr square, mr square. Distance, moment of inertia depend on the distribution. So more it is, the more is the distance from the mean position, more is the moment of inertia. So you just remember in this case, moment of inertia is equal to ml square. Okay. So L plays a role there. So mass into distance square is equal to moment of inertia. So you replace your moment of inertia as ml square here. Okay. So your now omega square, and now you got omega is equal to mgl by ml square. Mm cancels. So omega is equal to g by l. Omega is equal to g by l, and omega you know is equal to 2 pi by t. Yes. Because in time period t it is covering 2 pi. That means velocity, angular velocity is equal to 2 pi by t. So you know 2 pi by t is equal to square root g by l. Okay. Then time period is equal to t. Time period t is equal to 2 pi l by g. This will go this side, this will go this side. So just remember this. Time period t is equal to 2 pi l by g, and frequency is just reverse of time period, which is frequency is just reverse of time period, which is 1 by 2 pi g by l. Yes. So this you can compare with the spring mass system. Just t is equal to 2 pi m by k. Okay. So like 2 pi m by k. So here you have to remember all these things. There can be any number of numerical values. Okay. So in spring mass system, time period is equal to 2 pi square root m by k. In pendulum, the time period is equal to 2 pi l by g. So you just remember this l and m, these things remains in the numerator for time period. Okay. So this is how we derive the time period of a simple pendulum. Okay. So uh, 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 now we'll solve one numerical on a simple pendulum. You take a picture. Okay. So with this, this is very, very important. Uh, though it may not be required for you to derive the time period, but if you know how it is being derived, it will always be easier for you to remember. Yes, that's why it is always necessary that you should know how certain things are derived. Then only you will know the importance of each and every term in the formula. Otherwise, without knowing the derivation, you won't appreciate what is the importance of each and every term in that formula. Okay? So, that is, we'll solve one numerical. So, you know what is the importance of torque, what is the importance of force. Okay, so when you are opening a door, if you apply the force at a distance from uh, from the location where the door is being hanged, then like the hinges, the more is the distance from the hinges, the lesser is the force you have to apply to open the door. That is dealing with the so linear motion creates distance, angular motion creates angle. So to create that angle, you have to apply less force if you are applying the force away from the hinge. Okay. So that is the concept of torque actually. Okay. So now we'll do a numerical on simple pendulum. What is the length of a simple pendulum which tick record which ticks seconds? Okay. So okay. which takes seconds. So we know T is equal to 2 pi L by G. From this relation, we'll get. So he is asking the length of a simple pendulum. So T square is equal to 4 pi square, 4 pi square into L by G. Okay. That implies L is equal to T square into G divided by 4 pi square. Okay. So this is the so the question is what is the length of a simple pendulum which ticks seconds? Okay, so uh, in this case, time period of simple pendulum which ticks second is 2 seconds. Okay, so you know in your clock. Okay, so you have a pendulum. Okay, you have a pendulum. Okay, so this pendulum uh, what will be its time period from going from here to here and going from here to here. Pendulum is going from here to here. Pendulum is going from here to here, so it will come from here, it will come like this, then it will go like this, it will go like this, and one period will get completed, one time period will get completed. Coming from this extreme to this extreme, then going from this extreme to this extreme. That is the time period actually. Yes. So the question is this pendulum in a table clock, in a wall clock or whatever. This pendulum, what is the length of a simple pendulum which ticks seconds? That means he is telling ticks second means from here to here it takes 1 second. This pendulum, the pendulum from going from one extreme to another extreme, it takes 1 second. So from going from here to here, it is taking 1 second. Okay, that means from here to here 1 second. Then from here to here, it is another 1 second. Right, right. So that is the time period. Starting from here, going till here, starting from here, going to here, till the initial position. That is the time period. Okay. So your time period is equal to 1 second plus 1 second, which is 2 seconds. Your time period is 2 seconds. Okay. Your time period is 2 seconds. Okay. So knowing this time period as 2 seconds, now your job is to, they are asking, what is this length of this pendulum? So in a wall clock or whatever, they are asking a pendulum which clicks time period as 2 seconds. Actually, it's the length of a pendulum which ticks seconds. So from here to here, it is second. Okay. So find the length of a simple pendulum which ticks second. That means its time period is 2 seconds. If the time period is 2 seconds, what will be the length of the pendulum? Okay. So it will be T is 2 square time period and G is 9.8 meter per second square. Right. So it only I am saying 2 square means 2 seconds square, right? Is 2 seconds square. 2 into second square into 9.8 divided by 4 into 3.14 into 3.14. Right. So it becomes 4 into 9.8 divided by 4 into 3.14 into 3.14. So the length of the pendulum, so 4 cancels. So it becomes 9.8 divided by 3.14 into 3.14. So almost 1, I think it will be. Length 3.14 into 1/4, that is also almost equal to 1. So it is 1 meter. To divide it, it will be 1 meter. So the answer is the pendulum which ticks 1 second, its length is 1 meter. Okay, so there can be n number of numerical on this. See this, how will some formulate n number of numerical? Your T is directly proportional to L. One. T is directly proportional to 1 by G. Or T is inversely proportional to G. That is another one. So somebody will ask you in your the exam, okay, if the length of the simple pendulum is increased by 4 times, what will be the effect on time period? So it will become like say T1 is directly proportional to 4 times in 4L, right? 4L. So that means it is square root of 4 is 2 square root of L. Okay. So your time period will increase by 2 because T1 by T, that is what you want. So it will be, because there will be constant K. So it will become 2 into root L divided by root L. So it becomes 2. Right. So somebody will ask you, okay, on the same pendulum is taken to the moon, what will be the time period? So moon, time period is inversely proportional to G. So on the moon, the G value is G by 6, right? Yes. G by 6. So it will become T root 6. So T is directly proportional to root 6 by G. Clear? So the time period will increase by root 6 times. Okay. So that will be the answer. Okay. So that means time period will increase. Okay. In the surface of the moon. So how the acceleration due to gravity and length of the pendulum decide the time period of the pendulum. That's how the takeaway from this numerical. So you can practice a number of numerical on spring and simple pendulum now. And for sure there will be 2-3 numericals on simple pendulum and spring, which are very very important. Okay. So next we'll do free damped simple harmonic motion, and then we'll do some forced vibration, and we'll study the concept of resonance. Okay. In your lab you might have done that resonance and all. So we'll do next simple the free damped vibration and forced vibration and resonance. So free till now whatever we have studied is not damped, all are ideal. So we'll study about damping, free damped vibration, and then forced vibration, and then concept of resonance from forced vibration. So these are the things only remaining. Only these two things are remaining. Almost every other things we have covered. So now whatever the snapshots you have taken, you have to refer it, and you have to refer to my recorded video, which is of very small duration. So you don't have to remember, go to the books and study it from the scratch. Just refer for 5-10 minutes, remember this formula, try to solve as many numerical as possible. Things are simple. Rather than going to the text and reading how is derivation. See, the time period derivation, lot of text and lot of explanations are given in the book. I have tried to summarize it to 5 minutes, how to derive. So that a lot of explanation I have put in 4-5 lines and I have explained. So you better refer it. Okay, Sringma system and simple pendulum. Okay, next damped free damped vibration, then forced vibration, and then resonance, which is a concept from forced vibration. You might have heard about soldiers marching on a bridge. The bridge collapsing. What is happening? The soldiers are applying the force at a particular frequency. So when the natural frequency of the bridge matches with the forcing frequency of the soldiers, then it will lead to resonance, which results in high amplitude of vibration, which lead to the collapse of the bridge. So that is called resonance. We will study about that. Okay. There are many other examples of resonance where you always try to operate in a situation where the forcing frequency is away from the natural frequency. So every system has a natural frequency of its own. So the forcing function should be away from the natural frequency. Otherwise, if the frequency matches, there will be resonance and it will give rise to the collapse of the system. Okay. Okay, we'll study in the next class. Okay. Thank you.